let's go over our morning chant, shall we? We've got subatomic particles, protons, neutrons, and electrons, right? What does the number of protons specify? Say it real loud. The elements, right? And if you have a different number of neutrons, what is that going to give you? Different isotopes. That's right. And that's what we're going to be studying today, if I ever get this computer working. And coming up soon, although we'll mention it from time to time, if you have a different number of electrons, what is that going to give you? Different ions. That's right. Okay. So if I were to give you this symbol, what element is that? It's sodium. Okay. And if I give you a symbol that looks like this, you should be able to tell how many protons, neutrons, and electrons there are. How many protons are there in sodium? 11. Now you can also see that from looking at the periodic table. You'll be learning about that soon enough. Okay, but the number written on top of the element in the periodic table, that's the atomic number. That's the number of protons. How many neutrons are in this particular species? There's 12 neutrons because they add up to the mass number, 23. How many electrons are there? There's 11. How do you know? Right, it's the same as the number of protons, and there's no charge written in the upper right-hand corner. So we know we have the same number of electrons as we have neutrons, because we have a neutral atom in this case. And if I give you this, instead, everything else is the same. It's still 11 protons and it's still 12 neutrons. But now how many electrons does this have with a plus? It has 10, because there's one fewer negative charges than there are positive charges. Okay? But it's the mass number 23. This is what is the mass of this particular isotope of sodium. If we were to look this up on the periodic table, you would have a box here, and the box has sodium written up here. It'll have the atomic number 11 written on top, and then it will have another number written below it. Now on our periodic table, that number is 22.990. It's not 23. This is a slightly different number, and that's what we're going to be talking about today. This number here is what we call the atomic mass. Sometimes it's called the atomic weight, but I like to call it the atomic mass. Those terms are used interchangeably. It's not just the mass number, right? Although you might be confused about that. And hopefully I will erase that confusion today. The mass number refers to a specific isotope. The atomic mass weight, this is going to be what we call a weighted average of all naturally occurring isotopes. That's the difference, and that's what we're going to be exploring today. All right, so this is the discussion we're going to have today. And I left you at the last lecture with a couple of mysteries from Mendeleev's time when he put things out of order because they didn't know about the difference between the atomic mass and the mass number, because they didn't know what protons and neutrons and electrons were at that time. So all they could measure was the atomic mass. Now I've circled two cases. Tellurium and iodine was the one I showed you in Mendeleev's time, where the atomic masses are actually not in order. We have tellurium at 127.6 and then iodine at 126.9. But our modern understanding of the periodic system is based on the number of protons, not the atomic mass. So where does this come from? Why are these numbers different? They're also different here for cobalt and nickel, same trend. Right? It has to do with the isotopes in nature, because the mass number, that is the mass, all right? The more neutrons you have in the heavier isotopes, they will have a greater mass. So if we take the average of all of the isotopes in nature, you're not going to have a number that's equal to the mass number. You're going to have an average of them. And that's what these numbers represent. Here's sodium, 22.990. Okay, so it's all the stuff of isotopes. All right, so isotopes as a definition, here you go. They're atoms of an element that contain the same number of protons. We know this now because if you change the number of protons, you have a different element. But they have a different number of neutrons, okay? And this only affects the mass. If it has that number of protons for that element, it retains the same chemical and physical properties of that element. And we all know about chemical and physical properties now. Here's another example of some isotopes. Usually you have more than one isotope of a given element. And oftentimes there's many, many isotopes, although not all of them are going to be very abundant. Most of them are radioactive, and we're not talking about radioactivity this semester. So I'm just going to be talking about the ones that are most abundant in nature. So if you do an experiment with neon and put it in this positive ray analyzer, which is an early mass spectrometer, you don't need to understand how it works. The point here is that you can separate the different isotopes based on mass. So let's separate the isotopes based on their different masses. And you can see that if we take a collection of neon atoms and separate them in this way, we actually get two different species being read out in the detector. One has a mass of 20 AMU, which is atomic mass units, by the way, AMU. This is all from the video, atomic mass units. We'll be talking about those in a little bit. Right now, just think of AMU as a mass, all right, as some weight, right? And we get some that are 22 AMU. And you can tell by the number of little balls that are drawn in this diagram that we have about a 9-to-1 or 1, 2, 3, 4, 5, 6, 7, yeah, 9-to-1 ratio. About 90% of these are of the weight of 20 AMU, and about 10% of them are about 22 AMU. Well, not about, are 22 AMU. So what we have here is about 90% here and about 10% here. Okay, so now let's take a look at those symbols. And by the way, these are called nuclide symbols, the ones that we've been working with at the beginning of the lecture here. So if I draw the nuclide symbols for these two species of neon, I'm going to draw them this way. Neon, how many protons does neon have? Take 10. And if you don't know, take a look at the periodic table. So I'm going to put a 10 down here, even though I don't really need to, because if it has 10 protons, it's neon, and I'm using the chemical symbol for neon. So it's a little redundant in that sense. You should get used to interpreting these, either with or without the atomic number written in the lower left-hand corner. But now we have two different species. We have neon 20 and we have neon 22. And that's actually how we say them if we're going to talk about them. If I write it with words, I would write this as neon 20, and this would be neon 22. Okay, now we know how to interpret this. If I were to write the number of protons, they each have 10 protons. How many neutrons are there in neon 20? There are 10. Very good, because they add up to 20. How many neutrons are there in neon 22? There's 12. And how many electrons are in either of these? There's 10 electrons because these are neutral, as I'm drawing them here. Okay, so if we were to just look at the mass of neon 20, we would say that's 20 AMU. And if we look at the mass of neon 22, we'd say that that's going to be 22 AMU. So what's the average mass then? If these are the only two isotopes of neon in nature, what's the average mass? Is it 20? Here, let's use our A, B, and C. You say it's, so A, you're going to raise your A card. If you say it's 20 AMU, you'll raise your B card if you say it's 22 AMU, and you'll raise your C card if it's 21 AMU. And if you think, I'll give you a third option, even though I didn't have enough index cards for a D. I'm going to give you a D option as well, which is you raise your hand, because it'll be none of these. But let's see, nice and high. So I see A's, I see C's. Okay, the average mass. I'm asking for the average mass of neon. Okay. Nobody wants to just raise their hand because it's neither A, B, or C? All right, one, we have one. Okay. All right, very good. So we have mostly A and mostly C. So A, 20. So somebody who said A, why do you think it's A? So he said because you have to take a weighted average of 90% and 10%. And that is what we'll be doing, okay? But if you do that, you're not going to get 20. Or did you select A because it would be closest to 20? Ah, closest to 20. All right, fair enough. Anyone else? That was actually a pretty good answer. How about those who selected C for 21? Go for it.
I changed my mind.
You changed your mind. Well, then don't answer.
So like my reasoning behind it was just like just from the average between 20 and 22.
Right. Okay. So one student selected C, but then changed their mind. But they selected C because they were just taking the average between 20 and 22. All right. And that's what you think about when you take an average. But the point here is what you said earlier. It's a weighted average. It's not a normal average. And that's the difference between the answer being 21, which it's not. It's not a normal average. It's a weighted average. And we're going to discuss what that means. I don't need to explain to you what a normal average is, right? Actually, why don't I go ahead and do it? Because it's important for you to understand what's going on here. So if we take a normal average, how do you do that, right? You add up the individual parts, 20 plus 22, and you divide by the number of things that you counted, right? That's how you take a normal average. Divide by 2, and that would equal 21. Okay. Now, let me just do a little bit of fancy math here. Actually, it's not that fancy. I'm just going to do a little manipulation here. This is the same as 1/2 times 20 plus 1/2 times 22. That's the same thing. Okay. And now I'm just going to turn that fraction into a decimal. All right. That's the same as saying 0.5 times 20 plus 0.5 times 22. That's what a normal average is. Normal means that everything is in the same proportion, or you're counting everything equally. Now, the point of a weighted average is that not everything is present equally. For the case of neon 20 and neon 22, they're present in a 90% to 10% ratio. So we need to take that into account. The weighted average, the math is just the same. We're just going to take the fraction, the decimal fraction of the amount of neon 20. So that's going to be 0.9, right? 0.90 multiplied by whatever the atomic mass is. Sorry, whatever the mass number is. For neon 20, that'll be 20 AMU. And then we're going to add that to the fraction that's neon 22 and multiply that by the mass, 22. And then add them up. It's the exact same math that I just did in red for the normal average, except this is now a weighted average. So 0.9 times 20, you can use that on a calculator or do it in your head, however you want to do that. You would get, what is it? This is 20.2 AMU. Now, if we were to look on the periodic table for that number that's written under neon, what do you suppose it will say? Where's neon? Here's neon. 20.18. That's pretty close, right? I was pretty, we're just using nice round numbers here. But notice that the weighted average for neon is 20.180 atomic mass units, right? That's the weighted average of the naturally occurring isotopes of neon. And the two most prevalent ones are the ones that I talked about, okay? So that's the difference between a weighted average and a normal average. All of the numbers that you look at the periodic table, those are the weighted averages because it has to do with the different abundances of the naturally occurring isotopes in nature. They will have different numbers of neutrons, but they are all species, isotopes of the same element. They all have the same chemical and physical properties. Now, another reason that the numbers don't come out exactly the same is I've been using the nominal mass of 20 and 22 for these isotopes. It turns out if we were to discuss things like radioactivity and nuclear chemistry and things like that, you would find an explanation for why it is. I'm not going to get into that. I would love to, but there's just not time. That the actual mass for neon 20 is not 20 AMU, it's 19.9924 AMU, and so on and so forth. And in fact, there's more than just two species of, or two isotopes of neon. And you can see what their abundances are over here on the right. Now here's a percentage, right? But I'm going to do the same math. Just draw it out a little bit more, okay? Now, percent, that's out of 100, okay? Percent. That's per. Per is divided by, dividing by century, 100, right? So this is divided by, this is per 100. We want these to be in our fractional abundance, all right? We need fractional abundance. So if you're given percentages, just make sure that you turn them into decimals, okay? But then the math, it's gonna look complicated, but it's no more difficult than simply taking your weighted average, which is where we take the sum of the masses and we multiply that by the fractional abundance. Okay, so let me just show that to you so you have it thorough and spelled out in front of you. For neon 20, all right, we have, here, I'm going to move this over a little bit just so everything lines up. Sorry, I know you just wrote that in your notes. So for neon 20, the mass now is going to be 19.9924 AMU, and the fractional abundance of that is 0.904838. For neon 21, we have a mass of 20.9940 AMU, and its fractional abundance is 0.002696. All I'm doing is converting the percentage to a decimal. I hope you all know what I'm doing. For neon 22, the mass is 21.9914 AMU, and its fractional abundance is 0.092465. Okay. Now, I'm not going to spend the time to punch this in my calculator and show you what the actual numbers are. You can do that on your own. Prove to yourself, right? When you go home and fill this out, these will all add up to, when I did it in my notes, I got 20.17980 AMU for my weighted average. And if we were to round this to 2 or 3 decimals, and by the way, when you're working with atomic masses like this, never round these to fewer than 2 decimal places. Keep it to 2 or 3 decimal places. Oftentimes I'll see students round their atomic masses down to the nearest 1 AMU, and that's just way too severe. Much too much rounding error there. So if I round this to 3 decimals, I should get this, which will match what we have in the periodic table. All right. And again, it looks complicated, but this is no different from the normal average that I showed you before. If I turned that simple arithmetic into a fractional abundance, all right, instead of 1/2 and 1/2, well, it's not 1/2 anymore. Or if we had 3 things that we were making a normal average of, each would be present at 1/3. So the fraction would be 0.33, 0.33, and 0.33. But these are not equal, right? We're told what the abundance is, so we just factor it in. But the math is exactly the same. Okay? The good old plug-in chug, all right? Just know how to do the math. Understand what the math is telling you. Because rather than just asking a question, do you know how to plug the numbers in and chug away, right? We might be thinking about what a weighted average is from a different perspective, like understanding what's going on here, right? We expect, just like one of the students answered, when you were told that 90% of it was neon 20, okay? 90% is neon 20. So we could just look at this and only 10%, right? This was our original 90% and our about 10%. And you can look at that and you can figure out about what the math should be, because you want to look at one extreme, you've got everything is at 20 AMU, and the other extreme, everything is at 22 AMU. If all of the neon was neon 20, we would expect to have an atomic mass of 20, right? And if all of the neon was neon 22, we would expect there to be, instead, the atomic mass is 22. But we can look at the periodic table. The periodic table tells us that it's 20.18 or 20.2. So you would expect, based on 90%, all right, that the actual weighted average, it's not going to be, this is where it would be if it's a normal average. But the weighted average would fall over here. And this is the actual average of what the abundance is based on the actual abundance in nature. It's about 20.2, what you would expect. It's about 10% of the way between 20 and 22. All right. As you're digesting that for a little bit, let's now use our cards here, and let's just reinforce some of these things. You know, there is an exam coming up on Friday, and I want to make sure you guys have lots of practice. So we're just going to use our ABC card, and let's make sure we know how to interpret these symbols. So this one here, first of all, just yell it out. What's the element? Magnesium. Very good. All right. So A, B, and C. How many protons are specified by that symbol? A, B, or C? Nice and high. All right. I see lots of the right answer, which is B. Very good. I don't think I need to explain this one anymore. How many electrons are there? Oh, that's right. The answer is up there too. B. Very good. Right. 12 electrons. And we have 12 protons. All right. Very good. All right. Let's get a little more difficult. How many protons are here? What's the element? Sulfur. How many protons? And how are you going to find that out? Okay, I see a lot of the same answer. That's good. All right, how do you find out? What's the answer? It's A. How do you get that? You look at the periodic table, all right? Because I do want you to know the symbols and their names, but you're not necessarily going to remember or memorize what the atomic number is, but you should always have a periodic table in front of you. Very good. All right, let's get a little bit more tricky. How many neutrons are in, what's Cl? Lauren, how many neutrons are specified by this nuclide symbol? See, there's 18 neutrons, because the neutrons, remember, the mass number 35, this is the number of protons plus the number of neutrons. So you got to do a little bit of math, okay? It's not 35, that's the mass number. So you have to subtract the number of protons from the mass number to get what the number of neutrons are. All right, once again, without telling you what the atomic number is, how many neutrons are in P32. What's P? Is it phosphorus or is it platinum? Or is it plutonium? Phosphorus. All right, nice and high. All right, I see a mixture. I see B's and A's. Nobody's picking C. Looks like there's more B's than A's. Some of the A's changed to B now, so mostly B's. Let's take a look. So how are you going to attack this problem? All right, you look at the periodic table. What's the atomic number of phosphorus? 15. And what's 32 minus 15? 17. So there's your answer. 17 protons. How many electrons? 15 electrons, because there's no charge. This is a neutral atom. It's not an ion. All right, very good. Let's see. Let's get a little bit more tricky now. Which symbol describes an atom with 4 neutrons? Think about this one for a minute. O stands for oxygen. He stands for helium. Li stands for lithium. And you notice that when there's 2 letters in the name, the first letter is capitalized and the second letter is lowercase. All right, what do we got? I see mostly C. I see only C. Very good. C is the right answer. Now, to get this, you've got to figure out first how many neutrons are in each one, and then, well, I guess first you need to figure out how many protons there are in each one. So oxygen has how many protons? 8. So how many neutrons are here? 8 neutrons. Helium has how many protons? 2. So this gives us 2 neutrons. And lithium has 3, which gives us 4 neutrons. Very good. All right. So I want you to read this question, all right, and then talk to your neighbor. Introduce yourself if you don't know your neighbor already. Hey, hi, how's it going? All right. And let's see if we can figure out which of those 2 isotopes, chlorine 35 or chlorine 37, which one is more abundant in nature, and how did you come up with the answer? Just coming up with the answer alone, you have a 50-50 chance. All right. So that alone isn't good enough. You need to come up with why you know that one is more abundant than the other. Have a little chat. Did I give you the percentages? I did not. All you got is this. And don't Google the answer, by the way. You can look at other resources, and if you know how to do it, you'll know what I'm talking about. But you can't just go online and Google the answer. So the question was, how did I come up with the abundance number from the previous examples? Those were taken from tables, from actual measured values. So they are given to you. And yes, as someone already asked, I'm not giving them to you for this problem. So you've got to figure out how to answer this question in a different way. This is not a plug-in chart. You don't need a calculator to answer this question. All right, let's, normally I want to let this go a little bit longer for you to logic this out, but I'm curious to learn, just a show of hands, who talked to somebody new just now who you hadn't known before? Nice and high. How did it feel? Terrible. Did it feel good? Not terrible. We're all friends here, right? You're all in lab together. You're all in lecture together. All right. I'm really trying to nurture a community of learning here in this classroom. All right. So we're going to be doing now and again some more exercises like this where I might just take a break and let you guys talk to each other. All right. And to try to logic this stuff out. And then some of you are going to see each other in labs. Okay. And then as exams start coming up, I'm hoping that maybe you'll make some new connections with each other and form study groups. That really is one of the best ways to study for this, is not in isolation, but in study groups. So I'm going to try to keep encouraging that. All right, who thinks they have the answer, the explanation? And I want to hear from somebody who hasn't spoken for a while. You way in back.
So I think 35.
He thinks 35 because
This number is close to
That is a very good answer. All right. So if I take a look at the periodic table, here's chlorine. All right. Here's number 17. That's the atomic number, 17 protons. And we look at the mass, the atomic mass down below. I see here it says 35.453. Okay. This is the weighted average. We just went through all that. So if the only two isotopes were Cl35 and Cl37, all right, we would expect that the one that's most abundant is going to contribute most to the weighted average. And the weighted average here is closer to 35 than it is to 37. Therefore, chlorine 35 must be the most abundant. Now, that only holds true if, in fact, those are the only two isotopes. These do happen to be the two most abundant isotopes of chlorine, but most of the time there's going to be other isotopes as well. Okay, in this case, chlorine 35 is most abundant, which means that it contributes most to the weighted average. Okay, meaning that the weighted average that we measure, that we see on the periodic table, is closest to the isotope that has that atomic mass number. Yes. So that's a great question. All right. So why not 37? Because 37 is, I'm going to try to paraphrase what you said. Well, there are more neutrons. There's two more neutrons here. Okay. But if chlorine 37 was more abundant, because of that, if you work through the math of the weighted average, and you can experiment with this with your own numbers at home. Okay. If you work through that, if chlorine 37 was more abundant, then that would be contributing more to the weighted average. And so the calculated weighted average you would get then would be closer to 37 than it is to 35. But because the calculated, it's this math up here. It's this same math, right? If you, even though in this case, see, look, neon 22, it's more massive than neon 20, but its percentage is lower. So it's not contributing as much to the weighted average. Okay. So when you work through the math like this, that's what I said before. It's one thing to just understand how to plug and chug. That's fine. But I want you to understand what this equation is doing and how to interpret it. Okay. And the interpretation is like this. You don't need to do the plug and chug necessarily to be able to assess which one is more abundant based on what you know this number represents. Right? The number you read on the periodic table. So did that answer your question? You had a question too? So okay, so too many neutrons and it's unstable. That certainly will be true. If you start studying nuclear chemistry, as I mentioned, a lot of isotopes are very unstable and they're radioactive. And we're not going to deal with radioactivity in this class. So the only isotopes we're talking about here are the ones that are stable. So when I say that they're present in nature, I guess that's worth saying, right? Present in nature means that they're stable. These are stable isotopes. If they weren't stable, if they were unstable, and that is if they're radioactive, then you wouldn't find them in nature because they decay. They're not there anymore. But again, we're not going to talk about nuclear chemistry. Okay, in the few minutes that remain, let me start breaching into the next topic here, which is related to all of this. So now that we know what isotopes are and what the weighted average is, now we're going to start using that information to start taking account of the atomic masses of compounds, not just of elements. And when we start going into some more complicated calculations moving forward, how to keep track of things, we need to know what their masses are. So this all has to do with things that we call atomic mass, molecular mass, formula mass, things of that nature. So let's just start with a little review. The atomic mass, that's what we just did. That's the weighted average. And that's of atoms, okay? So if we're just talking about atoms, we would be using the atomic mass, the weighted average. That's what you read off of the periodic table. And the units for that are atomic mass units, AMU. We'll talk more about AMU and what that means in the next lecture. But now if we start building compounds, right, using our elements to make bonds, covalent bonds and ionic bonds, okay? And there's two kinds of compounds that we can describe. We have covalent molecules, covalent compounds, and we have ionic compounds. Covalent molecules like H2O, that's a covalently bonded molecule. We'll be learning about covalent bonds and ionic bonds soon enough. Ionic compounds like NaCl, I already introduced you to NaCl. But we can come up with what the masses of these are as well. It's what we would call the molecular mass. Actually, let's put that up here. The molecular mass, well, if we want to know what the molecular mass of one molecule of H2O is, we simply add up the atomic masses from the periodic table. We've got 2 hydrogens, and each hydrogen is 1.00794. So I'll round that up to 1.008, right? So 2 times 1.008, that equals 2.016. And then we have 1 times oxygen, right? The atomic mass of oxygen is 15.9994, all right? So that's going to be 15.999, and we add them up. 15, 11, 10, 18.015 AMU. That's the molecular mass of H2O. If we have an ionic compound, we would do the same thing, right? We have 1 sodium and 1 chlorine. These happen to be ions, but we're going to just treat them as the atoms right now, okay? 1 sodium has a mass of 22.990. Oh, let's write that neater. 22.990, and 1 chlorine has a mass of 35.453. You add them up, 3, 4, 4, 8, 58.443 AMU. Now, in this case, though, we're not going to call it the molecular mass. We're going to call this the formula mass. And that just has to do with the difference of how we characterize ionic compounds and covalent compounds. You don't need to know that so much for now, okay? But I'll just, as a preview, formula mass, this is for a formula unit. This is what we have for ionic compounds. Whereas when we have a covalent compounds, we actually have molecules. So the molecule, that's the unit. All right, the molecule is the unit here, whereas the formula unit is the unit for an ionic compound. Don't worry so much about those names right now, right? It's the overall masses that I'm talking about here, all right? And we can add them up just by looking at the atomic masses from the periodic table. So we're going to continue through that on Wednesday's lecture and then talk about the mole and do a couple more calculations. So you might want to start bringing a calculator with you to lecture to help you do some of these in-class practices.